This beautiful day feels a lot like Nebraska. Any of you been to Nebraska before? It's a lot like Kansas, but windier. So this is like being home. Much fewer runses though here than there, but I digress. Creepy Screen is back. We've got new material for today, and as I mentioned a few minutes ago, this class is killing it with respect to turning things in on time. Everybody finished homework 3, so I get a chance to go over it and make clarifications if anybody's wondering why things were right versus wrong. Would it be helpful to go over it as a group, or do you have any specific questions that you might have? Okay, we'll start with the first one. Would it be helpful to go over it as a group? Yes? I figure too much review can never be bad, right? Even if you're bored, like, isn't that a comforting thing to be like, yeah, I got this. I got this. I'm with you. So yes, computational questions, I think, for the most part, went pretty well. I did have several interactions with folks thinking about how to figure out what the specific effect size is. And for that reason, your next homework 4, which is ready, rather than adding multiple parameters to the same model and then trying to figure out which one is responsible for which pile of variance, I am having you add them one at a time. So there's more models, but you can see more clearly based on your pseudo R-square results which variance term each fixed effect is supposed to be accounting for. So that may help give you a little bit more background in that process. Homework 4 is going to take longer, just as a heads up, not in terms of the number of questions, which is my usual ridiculous amount of questions. You know, there's just a lot of moving parts here to learn, but the models themselves may take more time to converge. So when I was running it, I think on my powerful computer, the longest it took was maybe 30 seconds for a model. But if you're running it on a laptop that has less power, then it may take a little longer. So if you see SAS like chugging along and you don't think it's working, just give it a minute. Those of you who've gotten used to just hitting run and running everything every time you run anything, don't do that this time. It will take a lot of extra time. So just a couple heads up on that homework 4. That is due in 2 weeks, so Friday before spring break. So we have, let's see, green questions went pretty well. So in terms of the results, yeah, there were only one question in section 1. What kind of likelihood are you using? So there's a giveaway there. If you had gotten all the answers right, you would know that one. So I asked you to do person mean centering to enter the effects of stress. This is the method by which we are differentiating between person variance from within person variance in the stress predictor ourselves. So between person is level 2, within is level 1. So then the first question here, and something that is absolutely imperative when you're writing results sections, tell them how you set up your variables, because then they'll be able to follow why they mean what they do. So between person variation and stress was represented by the person mean centered at 5, which was your instructions. The centered at 5 is just because 5 was near the middle of this fake variable. Near the middle is good enough for any choice. Just make sure that 0 means something whenever you're centering predictors at a constant. Whereas within person variation and stress was represented by stress at each month centered at each person's mean. So several of you ended up with an incorrect intercept down the road because you had centered it at the person mean centered at 5. You don't need to do that. It's like centering it twice. So if you center the within person variable around the original person mean, then you can have the interpretation that 0 is whenever you're at your own mean and the reference person is somebody whose mean is 5. So then any effects of between person stress when it's entered only as a main effect are going to be overall, level 2, across time, whereas effects of within person stress at level 1, because level 1 is time, the within person effect of stress is at that occasion specifically. So there were a couple questions looking to make sure that you kept track of that distinction. So we're adding 2 fixed effects of stress. And this time, the reason that I gave you maximum likelihood as an estimator is so that you would have more practice in doing model comparisons involving fixed effects. So only in maximum likelihood can you test -2 log likelihood differences for models that differ in fixed effects. You can't do that in REML. If you're in REML instead, what you can do though is a contrast statement, which gives you a multivariate wall test, an F value instead of a chi-square difference. So you'll get a chance to do both versions of those in various assignments. So we added 2 effects, so that means the model got better or not better as a function of whether or not that was significant. And your homework is designed so that all of you follow the same story, so you all would have found that it was significant. The between person effect indicated that it should be well-being across the study, whereas this person's that I'm looking at here incorrectly put well-being at month 1. Now, why isn't it month 1 specifically? Anybody know? Who got this one right? I know some of you did. A few of you did. Okay, Lucas, why? Why isn't it month 1? That is true, but that's not why. Between person is entered as a main effect only, right? Does between person interact with time? Between person stress? Nope. So that's why. It predicts the intercept equally across time because it doesn't interact with time. If we had between person stress by time as part of the model, then it would be well-being at month 1 specifically, just like for age at baseline and treatment group, which both interact with time. So it's well-being across the study for the between person. Because between person is level 2, its main effect should account for random intercept variance. The within person effect then is level 1, which means it's well-being at that occasion. And level 1 accounts for residual variance. And then I had several questions about this smaller versus bigger. I'm talking in terms of absolute value effect size. So the closer it is to 0, it's a smaller effect. Even though it might be a more negative number, which is technically smaller on the number line, the interpretation that goes with that is that closer to 0 means a smaller sized effect. The further you get away from 0, either positive or negative, is a bigger effect. So in this case, if we look at the between person effect was -0.3, whereas the within person effect is -0.5, so that one is bigger. So the between person is non-significantly smaller, as indicated by the contextual effect, which is the test of the difference. Yes, question? Where does what? The contextual effect was requested right here. So if you found that number, you should have found a p-value for it. It will be an estimate statement in these models because you get the between and within directly. The contextual effect is the difference between the two. So that would be between 1, or wait a minute, let's say it different. -1 for the within and 1 for the between. Yeah, the order matters for this. And let's see. We added the within person effect of stress as a random effect. So going back over the terminology we did last time, only the within person effect of stress could be random, right? Because within person effect of stress is a level 1 variable whose variance across people occurs at level 2. So the within person effect, because each person has more than one set of values with which to draw a line through their stress effect, they can have a different line than someone else. So the level 1 within person stress effect can vary randomly over people at level 2. And because we already have 3 random effects in the model at this point, we have random intercept, linear time, and quadratic time. We've added a 4th random effect, and that means it's degrees of freedom 4. We've added the random slope variance for the within person stress effect, plus its 3 covariances with the terms that are already there. So then here's your confidence interval. So on average, there is a negative within person stress effect but that could be anywhere from a lot more negative to a little bit positive if you work out the 95% confidence interval. All right, any other questions so far? Okie dokie. So then we examined how the effects of stress differ between control and training groups. So we're examining moderation of the effect of stress at both levels by group. So given that the control group was the reference, the main effects of stress between and within that show up in the model are specifically for control. The interaction of each stress variable with group is the difference in the stress effect for treatment. And so then you would need to write an estimate statement to get what it is in the treatment group and the training group. And so this format here, I'm deliberately trying to get you to recognize the pattern. This for the control group is what you get from the model. That's the simple main effect of between person stress given the interaction with group. Here's what it is in training, which is the simple main effect plus the interaction. So the difference between the line that would have written this and the line that would have written that is just the interaction term. So the interaction term will tell you a group difference, and it will tell you whatever the effect in question is for one of the groups, whichever is the 0. You can add them together to get what it is for the other group. Same thing with within. So in this case, the specific effect sizes. So between person stress accounted for intercept variance. As a main effect, the main effect of group would have accounted for intercept variance. Therefore, between person stress by group would have accounted for intercept variance. Between person stress and group are both level 2 predictors, so that is a purely level 2 interaction. That makes it an intercept predictor. Within person by group is responsible for the within person random slope variance. So the within person stress effect represents individual differences in people's reactiveness to stress. Part of that may be due to which group they're in. And the story in this case, I thought, is that meditation training, which I am incapable of doing, but which I hear is really good for you, should reduce your responsiveness to stress. So, or mediation training, as it were. Both of them seem like they should be good for you. Yeah. So then we have the effect of having more stress than usual. That's how I would describe the within person effect, and that is at the same month, so that's the level 1 effect. And we talk about then how that differs between groups, as well as how the between person effect differs between groups. Between person still doesn't interact with time, so it's still well-being across the study instead of well-being at month 1. And then last but not least, these questions down here, looking to make sure you understand the principles of conditionality. General rule, each term is only conditional on the predictors it interacts with. So in this model, the linear rate of change, that's the linear effect of time. The linear effect of time did interact with baseline age, so it should be that one. It did interact with group, so it should be that one. It did not interact with between person stress. So that's what makes it this one, 30-year-old in the control group. Likewise, the quadratic rate of change interacted with age and it interacted with group. It did not interact with between person stress, so it's the same answer. Between person stress only interacted with time. Or, excuse me, group. I just misspoke. Didn't interact with time. Yeah, question? Mm-hmm. Yes, you and a lot of other people, by the way.
So where we center that has nothing. It's more just the value of the variable itself.
It's not conditional on itself unless it interacts with itself. So if I had person mean stress 5 by person mean stress 5 as a quadratic between person stress effect, which I could have had but didn't, then it would also be conditional on person mean stress 5. Just like we say that the linear effect of time is conditional on a particular occasion, when you have a quadratic effect of time, it would be the same rationale. But it's not conditional on itself unless it interacts with itself. So for this one, it's just the control group. And likewise, for the within person effect, it's just the control group. And then going the other way, which things interact with time. And in this case, the intercept is conditional at month 1 because everything makes the intercept conditional. The linear rate of change is also conditional on month 1 because of the quadratic rate of change. The quadratic rate of change, though, is unconditional. It would only be conditional on month 1 if there were a cubic rate of change in the model as well. And then down here, which variables interacted with time, baseline age, and meditation group. The end. All right. Any other questions on why it is what it is?
Can you go over why in month 1 the intercept is conditional?
This one? Yes. So the intercept is conditional on every single predictor where it's 0. So the intercept would be conditional on everything in the model, including time. Okay. The linear effect of change, linear rate of change is conditional on month 1 because of quadratic change. Yep. Other questions? Okie dokie. Then yes, so just to give you a preview, I know normally the Mondays after an assignment, this is your one point in time where you have nothing to do, but since this one took a little longer and because we're hitting up on spring break in case anybody wanted to knock off early and not finish their assignment on the last Friday, then you get a chance to do that. You can start on homework 4. So this is a story much like the crossed words and people example. It is children and toys. And you are going to end up with lots of random effects, and that is why the models take a longer amount of time to converge. And so I tried to be as explicit as possible. This time trying to make my wording more clear than before. Like enter the test statistic for the change in model fit after adding a random intercept, for instance. So trying to clue that this is a new model with a new term. And likewise here, change in model fit after adding this. Or what is, enter the -2 log likelihood for the model including this. So at every step you're adding something. You're never going backwards, okay? And it's the usual stuff. So let me know if you have any questions on that. All right. Are you ready for some new stuff that's not really new? So this is 2-level models for clustered data. And I swear to you there is only one new concept in this entire lecture. It's 44 slides that you've heard before, but you've heard it in a different context. So this is the first time in which people are not level 2 anymore. People are going to be level 1. So it's still true that we have level 2 between and level 1 within. It is still the case that level 2 means random effect variances, intercepts, and slopes of level 1 predictors. But now what between and within mean is between and within group. So the term is clustered data, otherwise known as nested data or any kind of grouping. And so this is a situation in which, for whatever reason, people are in groups and they come that way. It's not because of something that you did. We're not talking about control versus treatment. We're talking about existing groups, such as patients in hospitals, kids in classes or schools, people in families, that kind of thing. Even if you don't care at all about the groups, they have to go in your model. So these are ways of doing that. We'll talk about fixed and random effects, and then assuming you want to do random effects, which this is the topic for the day, we'll talk about how to do that. So here are two options for how you can represent group differences, fixed or random. So let's say that you're doing a study where you have a population that's hard to come by. And so you partner with some other sites, and you get your population from, let's say, 5 different places. Your people, because they already were part of those sites, may be different because of what site they belong to, for reasons that you have absolutely no interest in. That is a case in which controlling for site group as a fixed effect makes a good deal of sense. There's not very many. Less than 10-ish is the conventional wisdom. You don't really care what makes one different from the other. You just need to be able to control for group differences. So if you put in site as a class variable, meaning put it in as a grouping variable, that controls for intercept differences between groups. If you put it in as an interaction with any of your other predictors, that controls for group differences in the effect of that predictor. This is totally fine. The only drawback to this is that you can't predict what makes one site different from the other with site level information. But if you only have 5 sites, that's not going to work anyway. So this is just as well. Random, then, is the other option. And you go this route, you are adding a level to the model, meaning that you are saying that people are nested in groups, and you give groups, at a minimum, a random intercept and potentially random slopes. So these procedures are analogous. The idea of controlling for a main effective group as a set of fixed effects is analogous to adding a random intercept variance instead. The idea of adding group by predictor interaction terms is analogous to adding a random slope for the predictor instead. The advantage of the blue side, the bottom, random effects, is that you can then include group level information as predictors for why some groups do differently than others in intercept and in slope. So if you're interested in not only controlling for the effective group, but explaining why it's there, that's random effects. If you just need to control for it and you don't have that many groups, or you don't care, or you want to make an inference about a specific set of groups, that's fixed effects. So, any questions on that? Yes, ma'am. Well, you can, to the extent that you can say what it is that makes the groups different in only that dimension. So like if you have group ABC, you can let A, B, and C be different. But what it is that makes them different, how many other ways do they differ besides the fact that they're A, B, and C? That's the inference problem. Unless you had absolute control over why they're different, it would be really hard to be able to predict why they're different with other information besides just their ID. 10-ish is the recommendation that's provided. I've seen this a couple different places, and they provide absolutely no data to support it, by the way. It's just 10-ish. To me, it's more about the inference you're trying to make. So you can have more groups than 10 and still have a good reason to do a fixed effect model if what you're interested in is how each group does. So I can think of a couple examples. Lucas, I'm calling on you. You have country level stuff, right? Or religious groups?
I do.
You have both.
I was involved to just doing the US because it got pretty unmanageable. But yeah, I ended up having people in 11 to 15 religious groups.
Okay, so if you want to know specifically how Catholics differ from Muslims, differ from, you know, what all the other groups you might have, right? If you want to be able to make an inference about a particular group and how it is relative to other groups, then that's a fixed effect because you're caring about those specific values. Instead, if you wanted to know if groups that have this characteristic as part of their culture differ from these groups that don't, And multiple groups might have the same characteristic. That's random effect, because then you're trying to explain why they differ. If you're doing country stuff, like if you want to say, why is Sweden different than Norway? Right? Or why is the US different than Germany? Right? If you want to make specific inferences about these things, giving each country its own fixed effect via a dummy code allows you to do that. But if you want to know if countries who have more egalitarian attitudes differ than countries that don't, right, then that's a country level predictor that would then explain why the random effect for country is there. As another example, so I think I've told you this story before in this context, but I'll give you another example. My husband around this time last year got super famous. And by super famous, I mean like the local news wanted to interview him, and so did the Kansas City newspaper. And the, what is our KU student paper? I'm getting all the places I've worked confused. I want to say the DNL, but that's not it. Daily, it's not the Daily Nebraskan. That was my previous job. What's it called? Daily Kansan. Oh, close enough, right? The Daily Kansan. I got to actually be a source in that article. But it was March Madness. And he built a website to predict the brackets and who was going to win. No, for real. I think it's still on his website somewhere. And he was like one of the few people who predicted that Gazaniga, or whatever the hell it was called, is going to win, right? And they did. And so he got all this, you know, press. And he did it with a fixed effect model for team. So how many NCAA basketball teams do people keep track of? What, hundreds maybe? At least 100. Lots, right? Way more than 10. Can we agree on that? Way more than 10. And so his models were multivariate models predicting who was going to win each game using dummy codes for who was the home team and who was the away team as fixed effects. Because he wanted to be able to make predictions as to how KU would do against Duke, as opposed to why is it that some teams score more points than other teams, right? Those are two different questions. So that's an example of when a fixed effect is more useful because you want to make the inference about that specific unit and how it compares to other units. So if you want to know what the differences are between your units, that's fixed effects. If you want to know why the differences are, that's random. If you don't have at least 10 units, good luck trying to figure out why. You can try. It's not going to go well. So this is if people think about people nested in treatment groups, so like the example that we had in homework 3, treatment versus control, that's not a 3-level model. That's not this. Because we only had one control group and one treatment group, and once we put in who is in which group, that's all the variation due to group there can be. If I had, say, 6 control groups and 6 treatment groups, that is then we're talking about this. Because then we'd have to decide how the model is going to build in terms to say why not all the control groups are the same and why not all the treatment groups are the same. So if you have variation left over after putting in which group is which, that's when this is relevant. It's not relevant if you only have one treatment group or one control group. Okay, with me? Questions, thoughts? No? No thoughts? None you want to share, at least? Okay. All right, so here's your empty model for clustered data. It looks remarkably similar to the empty model you already know. Can you spot the difference? We'll play Where's Waldo for letters. J. IJ. Not TI, and I do this very grudgingly. I'm a big fan of using subscripts that actually mean something. And so if I had my druthers, I'd say IG for group, but the entire world uses IJ. So just think of it as J for group spelled wrong. I say G and J interchangeably sometimes when I'm spelling things aloud, so I may actually say it that way, but yeah. So individuals are the I still, they're level 1. J is group spelled wrong, level 2. Otherwise, the notation is exactly the same. And this helps to explain why it is that E is level 1 and U is level 2. This comes from what it would look like if you had a single level regression model of people. The E term would be between person differences. When you add the multi-level component, you're adding the groups, you're adding the U. So that's why E is level 1 and U is level 2 in most people's notation, is because the world of multi-level started out, I think, more this way than the longitudinal way. But this is our empty means random intercept model. 3 terms: fixed intercept, which is the mean of the group means. Level 1 E variance, residual variance, which is now within variation of people within the same group. And level 2 U variance, this tau squared, which is differences between groups. Otherwise, it's all exactly the same. Interclass correlation works the same way here. In this case, though, we will never have an R matrix that we do anything with. So this R matrix, this is for one group. So it'd be like, this is the variance across person 1 and person 2 and person 3 and person 4. But person 1, 2, 3, 4 doesn't have an inherent ordering the way time 1, 2, 3, 4 does. Any one of the people could have been 1, 2, 3, 4. So there are no R matrix structures that make sense in this context other than VC, because people are exchangeable. So we will not ever have a repeated line because we don't need it. We'll only have a random line where the subject is the grouping ID instead. So each group will get their very own V matrix that has as many dimensions as they have people. So if they have a group of 10, it's a 10 by 10. If they have a group of 3, it's a 3 by 3. A question I get fairly frequently is, what happens if you have a group that only has one person in it? Can you keep it in the model? Yes, you can. However, be aware that that person's variance goes to the group level. So you can end up with interclass correlations that are somewhat biased if you have a lot of people in your sample where there's only one person per group, because it will look like there's a lot more group variation because there isn't a way to distinguish it. So yes, you can have people with only groups with only one person in the same way that you can have people with only one occasion. Both are true. Yeah?
You mean there are only one person in one group, so the variation becomes group level?
Yep.
There are only one person, where is the variation?
With one person, that person's variance goes to the group level because they are their group. Yeah, it's counterintuitive, but that's where it goes. So you can end up with stronger group effects because of that if you have a lot of those types of cases in your sample.
So the group effect becomes stronger.
Group effect becomes stronger, yes. So intraclass correlation, we said it's the proportion of variance that's between, right? Still true, but now it's between groups. It's also the average correlation of people from the same group. And it is still an effect size for how much of our variation is due to group dependency in the intercept. Some people like to look at this number and make up rules for at what point you need to care. Like an intraclass correlation of 0.05 or bigger needs a multi-level model, but anything less than that doesn't. Nope. Nope, 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 nope. Here's why. Here is the one new concept for this entire unit, folks: design effect. Statistically, it is the ratio of the variance using a given sampling design to the variance that you would have had using a simple random sample from the same population given the same total sample either way. In English, it is an index of how screwed you are by your clustering. That is what it means. So the formula for design effect is 1 plus the number of level 1 units minus 1 times the intraclass correlation. So only when the intraclass correlation is exactly 0 is your design effect 1, meaning that your ratio does not change your sample size, and the sample size that you have is really your effective sample size. To the extent that you have a greater number of people in your group or a greater interclass correlation, the actual sample size that you have is less than what you think it would be. A lot less. So chapter 13, the first section of that, goes over this and talks about how you can use this formula to do some rough power calculations. So N effective is the real amount of sample size you have in terms of your power. It's the number of total observations that you have divided by the design effect. So best case scenario, if you have one person per group, meaning you don't have clustered data, or you have an intraclass correlation of 0, then your design effect is going to be 1, and the number of total observations you have is the same thing as the amount of effective observations you have. So let's think about this in the context of dyadic data for a second, right? Couples, 2 people per couple. Best case scenario, if I have an intraclass correlation of 0, I have no between couple variance whatsoever. It's as if I have a study of people, not couples, in terms of my sample size. However, let's say that I have an intraclass correlation of 1. What would that mean? What's an interclass correlation of 1? All between, which would give me a design effect of 2. So my effective sample size is the total number of people divided by 2, which is the number of couples. So if I'm thinking about how to power these things, the amount of subjects that I have in my sample, even if it's for person level information and not couple variables, if the intraclass correlation is 0, I have the power up to the number of individuals in the sample. If the interclass correlation is 1, I have power up to the number of couples. Somewhere between the number of level 1 units and the number of level 2 units based on the interclass correlation. So more observations per level 2 unit or in a higher interclass correlation, those things work against you in terms of how much power you actually have at level 1. So for instance, let's say that I recruit 5 patients from each of 100 doctors and I have an intraclass correlation of 0.3. So 30% of the variation has to do with which doctor. So you would think that I have 500 patients. That seems like a lot of power to detect patient-level predictors. But the design effect works out to be 1 plus level 1 sample size minus 1 times interclass correlation, 2.2. 500 by 2.2 is my effective sample size. 227 people is the amount of independent information I have. So that means if I were interested in studying patients, I don't care all about doctors, but I have to get multiple doctors worth of patients to get enough people, and I run a power analysis that says I need 227 people in my study. If this is my sampling plan, I got to go out and get 500 instead. The higher that denominator is, the higher that design effect you have, the more screwed you are by your clustering, and the more subjects you have to recruit to overcome it. Here's another example of why rules like an intraclass correlation of 0.05 or less is ignorable. Nope. What if I have 20 students from 50 schools and an intraclass correlation of 0.05? School variance is tiny, right? It's only 5% of the story. Can I just run my regression? No. My design effect works out to be almost 2 in that case, which means I have half as many people as I thought I did. So very small interclass correlations can still create relatively large design effects if they occur in samples in which there's a lot of units per level 2 group. So this is something that you can use in terms of planning research. It's not as useful after it's conducted, but this is helpful for anticipating what the effect of clustering is going to be on your power. So if you're thinking about this, say, in a longitudinal context, power for time-varying predictors would follow this formula. It's going to be somewhere between the total number of level 1 observations that you have, best case design effect of 1, and the number of people that you have at level 2, worst case if you have a fully non-independent sample. So somewhere in the middle is usually what your actual effective sample size is going to be. Okay. Does that make sense? Okay, and I have spreadsheets, by the way. I'm happy to share with you. I do these sorts of calculations all the time for power analyses and grants. What you need to do is to be able to anticipate what a reasonable intraclass correlation is based on your outcome, a range of it maybe. If you think it might be about 0.5, maybe figure from 0.4 to 0.6, and you can decide how many units you're going to have at level 1 and level 2, and you can play around with what are the optimal combinations, trying to figure out what the right balance of level 1 and level 2 units is. There's also software online you can find that's free. Optimal Design in particular is a program that helps figure out these sorts of level 1 versus level 2 sample size in the context of a budget. So like if you know it takes X amount of dollars to recruit a new hospital to participate in your study versus more people in the hospital, you can factor in those kinds of budgetary concerns into the software, so that makes it handy for anticipating these sorts of studies. It's called Optimal Design. It's Radenbush, and I think, I want to say Spybook or Sprybook is the first author on the tech manual that comes out of it. So if you ask the Google about that, I'm sure you can find it. I think I have references to it actually in my book too, in chapter 13. So here's another one. What if your interclass correlation is non-significant? Now you guys know how to test if it's significant, right? I made you do this like 8,000 times? Maybe, roughly, give or take? How do I know if an interclass correlation is significant or not? From an empty means random intercept model. Step 1. I'm like, what's the ICC? Give me the test statistic for whether it's greater than 0, right? What's that? Where does that come from? Nobody wants to talk. You all know this. Why am I getting these looks? What did I do? Now you're smiling sheepishly. Everyone looked really mad at me for a minute. Like, I know my homework sucks, but trust me, in a few years when you actually know how to do this shit, you're gonna not hate me anymore, I hope. You can hate me today, that's fine, but answer my effing question, because I know you guys know this. I don't ask questions that I don't think you know the answers to. Yeah, likelihood ratio test, right? Does it show up on your SAS output for you in this one instance? Yes? I know you know this. I know you do. It's a test of an empty model that has E-only residual variance versus one that adds a random intercept. And yes, it shows up as a null model likelihood ratio test on your SAS output, and it shows up as like LR test against regression model or something in Stata. That's what it's called. You get that by default. SPSS doesn't give you that, of course. And you can end up with intraclass correlations that are not significantly different than 0. So a reasonable conclusion might be, okay, does that mean I can just bag my multi-level model and go back to regression? Because if there's no group variance, then do I need to worry about measuring it and predicting it? Nah, you would think so, but what happens when we add level 1 predictors that explain residual variance? What happens to your random intercept variance? You answered this last time, Claire. I'm calling on you. Goes back up. So you can end up with a non-significant intraclass correlation in an empty model that becomes significant and sizable after residual variance is explained, bumping it back up. So then you may have a non-ignorable group dependency in your intercept, and you may also have group dependency in your slopes. So yes, in practice, even if you have a very small or even 0 intraclass correlation to start with, leave it in. Leave it in until you are all the way done modeling everything and see if it ever comes back and changes your inference. If it doesn't, that would be a good argument for maybe just running the single level model. But to cover your bases, don't start with that conclusion because your answers may change. And if we have any kind of group level variance that we have to worry about, then we have to worry about contextual effects as well. So in terms of predictors then, level 2 predictors are now group things. They explain random intercept and slope variance. Level 1 predictors are people things. They can have a fixed effect. So for instance, we're going to have We're going to look at math scores as a function of SES. Here's an example using gender. So is there a gender gap? Is there one? Yes or no? That's a fixed effect. Does the gender effect differ as a function of school predictors, such as rural versus urban? If so, that might be a systematically varying gender effect. And does each school or group need their own gender effect? That's a random effect. And we can quantify how much group level predictors then reduce that random slope variation. Now, the nice part about clustered data is there's about like 11 weeks of material that we talked about stuff related to time last time that we can just skip here. There's no time. So you go straight from empty model to the models you care about that have your predictors in them. So we have the same set of concerns with respect to smushing in clustered data as we did in longitudinal data. Each level 1 predictor, to the extent that it has an intraclass correlation greater than 0 and less than 1, has variation at level 1 and level 2, and it belongs at both levels of the model. So within group variation in SES, for instance, some kids may have more money than other kids in their school, and some schools, if you were to aggregate, say, whatever you're using to indicate SES, some schools are going to have more rich kids than others. So if we were to look at the effect of student SES, even if we don't care about the school per se, we can't ignore the fact that there may be school level variance in it, and that school level variance goes in the model. So there's examples then of how you may have between and within effects going the same way. So generally more money means higher achievement. Here's an example from a annual review of psychology article talking about it in the opposite directions. So between groups, larger species tend to have longer life expectancies than smaller species. So whales live longer than cows, who live longer than ducks. But within a species, relatively bigger animals have shorter life expectancies. So it works in the opposite direction in terms of how size predicts life expectancy. And the same thing is true here. These are unstandardized regression coefficients on different scales. So for that reason alone, your between effects and your within effects are not going to be the same number. So your options for how we differentiate the effects of a predictor at level 1 are the same. Before we called it person mean centering. It's now group mean centering, but it's the same idea of using a variable. So you can create a level 1 predictor I'm calling within group X that is purely level 1 within group information by taking your original level 1 X and subtracting the group's mean. Or you can use grand mean centering or no centering, in which you center at a constant. And the same differences that we learned about before between versus contextual versus level 1 versus smushed effects happen in this case. So we have, here's an example of group mean centering. So the within group version of the variable has only level 1 within group information. The group mean goes in at level 2 and it carries only between group information, and their coefficients then align exactly. The level 1 predictor carries the within effect, the level 2 predictor carries the between effect, the end. The other one then is the contextual effect. So just to remind you why these are different, the same level 2 predictor goes in either way. The group mean, centered at a constant so that 0 is meaningful. So this column, for instance, right here, here's a group that has a mean of 3 and a group that has a mean of 7. The rows are for individuals within the group. Within group centering at level 1 would get rid of all of those absolute group differences and contain only relative within group information, whereas if instead you center at a constant or even leave it uncentered, both relative and absolute information are still there. So then the effects are different if you put in this level 1 X variable with group mean X when they're together than when they're apart. So this is the wrong version, again, smushing. Level 1 X put in all by itself, that's wrong, right? When I do this, what am I assuming about the effect of my X predictor? Same effects within as between. Said differently, I'm assuming there's no contextual effect. So to fix it, I can put in the group mean at level 2, which then carries the contextual effect. And it makes a lot more sense in this context. And for that reason, I think it is a lot more common and potentially more useful to set up your model this way. So the contextual effect tells you, after controlling for the effect of the person, after controlling for whatever characteristic at the person level, what is the extra incremental additive contribution of the group? That's the contextual effect, and that's level 2. It's the extra effect that is not extrapolable from your individual information. So what is the effect of going to a rich school, for instance, after controlling for whether or not you're rich? What's the effect of living in a country that has this characteristic in general after controlling for your version of the characteristic? Those are the kinds of questions that contextual effects allow you to answer. It's still the case that if we take level 1 and add in the contextual, we get back to between. So you get either one using an estimate statement that you want. So this is all literally like the exact same lecture we did like 2 weeks ago, just with IJ instead of TI. The trick is recognizing the same issues in a different context. So here's my context. Here's example 6A. This is one of my favorite data examples because it is 100% real. I did not mess with these data in any way. They came straight from an end of 10th grade math test in another Midwestern rectangular state. I will let you guess which one. So I am using data from 13,802 students from 94 schools, somewhere between 31 and 515 students in each school with an average of 275. I deliberately made it so that no schools in this sample had fewer than 30 students. I did that just because I was going to be using student level information at the aggregate to represent school level information. That's just an arbitrary choice that I made. The school level predictor that we have for math here is whether or not the kids get free and reduced lunch. 0 means they pay for their lunch, and 1 means they get some kind of discount. So this type of information would be available at the school level, most likely from another source. Schools would know what their proportion of students getting free lunch would be, and that would be a far better school level, level 2 representation of this variable if you had access to that kind of direct information. But I did not, because I borrowed this data and I didn't have any better data than that. So I took the average free and reduced lunch dummy code variable per school, and I stuck that in as my level 2 version. So anytime you have organizational level information that is more complete than just averaging the people you have in your sample, use that instead as your contextual effect. But here's what the code would look like to do that. Now this is one of the examples that I used to do in my ICPSR workshops, which I did deliberately use 3 different programs in, so I just decided to put this version up. So if you would like to follow along in a different program for a change, knock yourself out. I only have SAS output, but you can find full output for everything electronically on the website for the class. So in SAS then, the first thing I did is run proc means by school, and I got school level means for my math outcome and for my free lunch dummy code. So because free lunch is a dummy code, the school means are going to range from 0 to 1, meaning 0, no students in the school get free lunch, to 1, meaning 100% of the students do. I merged those school mean variables back into my original data set, and I'm running descriptives on them here. And then in terms of centering, because free and reduced lunch is already a predictor that has a meaningful 0, I didn't center it, I left it alone. So 0 means a kid who pays for lunch. I did, though, have to center my level 2 predictor, and I centered it near the average, which was about 30% of the schools, a school, the average was that 30% of their students got free lunch. And here's the descriptive stuff here after the same code that exists on all the other programs. At the bottom of the second page here, So for school mean free and reduced lunch, which is the level 2 predictor I created, on average, 30% of the students in a school get free lunch, but that does range from 0, meaning that school has no kids who need help, to 80% of the kids need help. Now, I will remind you, this is real data in a Midwestern rectangular state. So that is a lot of variability even within a fairly stable population. Math scores, these are scale scores, and I have no idea what they mean other than that they mean something to someone, and they range from 0, meaning you didn't get any right, all the way up to 83 with a mean of 48. We have then school mean math, which I also outputted, has a school mean here of 48 with a range of 29 to 61. That's the school mean, varies that much. So that is foreshadowing the fact that we're going to find a relatively large intraclass correlation here. So here is my 2-level empty means random intercept model. I have 2 ID variables here. We don't actually need the student ID one, but I have it on here for completeness. School ID is my level 2. So now my subject is school ID on my random line. I don't need a repeated line. My R matrix is going to be VC forever and ever because students are interchangeable within a school. I'm saving my fit statistics and my covariance parameters so that I can do math on them later. And here is the same version of the model. I'm in ML, by the way. The same version of the model in SPSS and in Stata for those of you who would like to see it in another program. And here's what we got. So intraclass correlation, that's my random intercept variance divided by my random intercept variance plus residual. In other words, level 2 over level 2 plus level 1. Works out to be 0.15. So 15% of the variance in math has to do with which school you go to. So there are large differences in an educational context. This intraclass correlation is pretty big. Large differences between school and how the kids do. Given this intraclass correlation and the average number of kids per school, which was 275, I calculated a design effect that was simply unbelievable. It's 42. And I could have used different versions of this number, such as the geometric mean instead of the arithmetic mean, but it's still going to be a huge, huge design effect of 42. So when I thought I had 13,000 kids, I actually have about 311 when it comes to how much unique information they provide. I know, right? The first time I saw that, I was like, there's no way that's right. And I checked it like 17 times, and it's right. It's an approximation because not all schools have 275 kids, but it points out that even a small interclass correlation in samples designed this way has a huge effect. So I don't really have as many students as I think I do. I can calculate a 95% random